السلام عليكم يا اخوان كيف الحال؟ going to be solving, well, let's have a look here. Okay, so we have chapters 12, 13, 14 and specified past papers from Miss Lamita for the periodic. هلا in the actual exam related materials they don't specify any past papers, AP past papers for your response questions, but Miss Lamita specified questions and I have a strong feeling those questions are going to come. They just didn't want to put these past papers in the. So I have a speculation that they didn't want to put the past papers in the material so they could separate from like the lazy people and the non-lazy people. So I guess whoever listened to Miss and wrote down those past papers is gonna benefit because the written part might come from those past papers. So we have from 2011 up until 2021. It's a lot of past papers. I probably won't do them in this recording. This recording, I'm gonna try to finish chapter 13 because Salah has like the easiest chapter I could do right now, and yeah, I'll get with it. It's also like the shortest chapter. I'll also try to see if I can do chapter 14. I already, sure, I already solved, cha- I already solved chapter 14, so I don't think it'll be an issue explaining it. I just there's a few things I'm unsure about, or like not 100%. Like I'm not 100% about the chapter. I haven't fully solved it. There's like one or two questions that I'm, as I said, unsure of, and I don't want you guys like getting wrong information from me or like not fully benefiting from what I'm doing, right? Yeah. Anyways, I'm gonna start with chapter 13 because it's like it's like material we've done last year, and it's pretty self-explanatory, right? So, just give me a second, we'll begin. Okay, so chapter 13 is all about chemical equilibriums, and we've done this stuff last year. It's very, very easy and self-explanatory. It's just you have to understand the topic, and then they're going to ask you several various ways on how to apply the understood topic. So, equilibrium, yeah, chemical equilibrium. First question. Given 2SO2 plus O2 to give 2SO3, and the K equilibrium here is 2. Calculate the value of K for the following two reactions. So, we know that the formula for K is going to be, let's say we have reaction A plus chemical B to give chemical C plus chemical D, where the small letters represent the coefficient, right? The To find the equilibrium constant, it's going to be the concentration of the products over the reactants. It could be either the concentration or the pressure, depends on what they're asking for. So for concentration, we represent it like this. So for concentration and everything else, we represent it like this. So it's going to be with brackets, and you have to write down the brackets because these brackets represent concentration, okay? Concentration of the product to the power of the coefficient times concentration of any other products. And we only write down chemicals in the reaction that are either gases or they are in the aqueous state, so in a solution. Uh, yeah, and concentration of chemical D to the power of the coefficient over, and same goes for the reactants. We only consider gases or aqueous, so concentration of A to the power of the coefficient times concentration of B to the power of the coefficient. Now, this is for uh, everything except K P. where Kp is represented like this. So you do P of so chemical C, where's chemical C, to the power of the coefficient, obviously, times the pressure of chemical D to the power of the coefficient over another reactant, so the pressure of chemical A over the coefficient times the pressure of B over the coefficient. Okay, so this is just get a general understanding of this, right? Now, let's look at the first question. They gave us the K for this formula is for this reaction is 2. So let's just write down this reaction. Let's just write it down in the form of in the form of the formula I just showed you. So this would be uh this is just K, so I'm just gonna write down K equals to yes, so SO3 to the power of the coefficient over 2SO2 and O2. We consider these since they are gases. So S SO2 squared times O2. Now, in the in part A, they want us to find K for this reaction. As we can see, let's see the difference between this reaction and this one. So, this one we can tell that the coefficients were all divided by 2. So, 2SO2 divided by 2 is just SO2. O2 divided by 2 is half O2, and 2SO3 divided by 2 is just SO3. So the formula will look something like this, right? So in this case, so originally the K was 2, right? For this, let me just write it down real quick. And then we basically did the square root. So to change from this from this formula to this formula, we basically just did the square roots, right? We got rid of the power here, so radical, so square root of 2 is 1, square root of 2 is 1, and square root of 1 is, wait, no, we didn't do the square root, sorry. Wait, let me phrase this properly. What they did here was they divided the coefficients by 2, therefore, the new formula is going to look like this, right? This is the old formula, this is the old one here, old, and this is the new. So, if this is equal to 2, therefore this one is going to be equal to radical 2, right? Because all the powers got divided by half. Sorry, got divided by 2. So 2 divided by 2 is 1, 2 divided by 2 is 1, and 1 divided by 2 is 1 over 2. Therefore, it's going to be radical 2. Now, part B, same thing, except here, instead of halving the coefficients, we multiplied them by 2. Therefore, it's going to look like this, right? I'm just going to write it down real quick. Oh yeah, 4, right? Yeah, okay. Yeah. So this one was 2. This one, we multiplied all the coefficients by 2, so all the powers got multiplied by 2. Therefore, we're going to square this, right? Because the powers got changed. So 2 squared is 4. So look at the answers. So radical 2, which is radical 2, 1.4, and 4 for part B. Now, write the equilibrium expression for the following reactants: C solid plus half O2 gas to give CO. We know that we shouldn't consider anything that isn't a gas or a chemical in the aqueous state. Therefore, the equilibrium expression for this reaction is just going to be CO, so concentration of CO over O2 to the power of half. Okay, this is, yeah, so either to the power of half or radical O2, both work. Write down equilibrium expression in terms of partial pressures. So partial pressure is just going to be um so here we have, they're all gases, so we're going to consider all these in the equilibrium expression. It's going to be the P, so the partial pressure of HI squared, because the coefficient is 2, over the pressure of H2 times the pressure of I2. That's it. Yeah, so pressure of HI squared over pressure of H2 times pressure of I2. Now, write Kw for H2O. I'm just gonna screenshot all these and solve them at once because they're very, very easy. Now, all of these you just write down. So you see how in the previous one, right? And the in the previous one, we didn't write down brackets since they asked for pressures. Everything that isn't equilibrium equilibrium expression in terms of pressures, we're going to write down, we're going to include the brackets. If they're asking for pressures, don't include the brackets, right? P and then the whatever, the chemical, yeah. So here, for this formula, so here we have a liquid, we don't consider this, so we just consider these two over here. So it's going to be the concentration. So this is Kw, right? Kw, since they asked for write the constant in terms of Kw. So Kw equals to concentration of H plus times the concentration of OH minus. Khalas, easy. This is part C. Part D. Uh, write down K for Ka. So here we have aqueous, aqueous, aqueous. So we consider all of these. I'll write down this somewhere else because it might need more space. So over here. So products over reactants. And here we don't have any reactants. It's just going to be like over 1 or just this. Okay, so CH3. Okay, so no, K here the dissociation of an acid Ka. So Ka equals to C, no, first of all, concentration of CH3COO minus times H plus over concentration of CH3COOH. That's it. Part E, same thing, literally just for a base. So here it's going to be Kb instead of Ka. So let's see. Liquid, don't consider it. Okay. Product of reactants. So Kb is equal to concentration of NH4 NH4 plus times the concentration of OH minus over the concentration of NH3. Let me just mute this so you don't always hear it. Okay. So we did part E, part D, part C, part F here. Write down K for KSP. So here, what do we have? Solid, don't consider. AQ and AQ. So KSP, this is part E. KSP is going KSP is going to be equal to the concentration of A write that better. Ag plus times Cl minus. Okay, that's it for this question. This is pretty straightforward. I was like, if you don't understand this, I hope you understand it now. Yeah, that was all of it. Okay. Okay, so a sample containing 2 moles of H2, 2 moles of I2, and 10 moles of HI were introduced into a 2 decimeter cubed vessel at a temperature where the following reaction occurred. So what are they asking for us here? So calculate the concentration of all the species at equilibrium, and equilibrium has an equilibrium constant of 10. Is the system above at equilibrium? If not, calculate the concentrations of all the species at equilibrium. So, first of all, we want to find the concentrations, right? They give us moles for each reactant and the product, and they give us volume. So, concentration of H2 is equal to 2 moles divided by 2 decimeters cubed, or 2 liters, same unit, same thing. So 1.00 molar. Concentration of I2, so same thing also because same number of moles, 1.00 molar, and then concentration of HI is just going to be equal to 10.0 divided by 2.00, so 10 divided by 2, 5.00 molars. Okay, so the reaction has an equilibrium constant of 10. Is the system above at equilibrium? If not, calculate the concentrations of all the species at equilibrium. Let me just double check of what I'm supposed to do here so I don't mislead you guys. Yeah, okay. So we just write down the equilibrium expression, which is going to be the products over the reactants. So concentration of HI squared over, this is HI squared over concentration of H2 times I2. And we already have the concentrations of every single one of these. We just calculated them here. So if you substitute it into your calculator, let's just see here. Hello, okay. So what is the concentration of HI? HI is 5 molar, so 5 molar squared, 5 squared over 1 times 1, which is going to be 1. And this is equal to 25, right? This is Q in this case, because this is the mass action expression, I believe is what it's called. This is to find out if the system is at equilibrium. So we got 25. Now, uh, we got this value to be 25. We want to figure out if the system is at equilibrium. So we're going to apply some rules. I'm just going to find the rules in my copybook since I don't have them memorized. Right, so if Q is equal to K equilibrium, that's G, not Q, then it's at equilibrium. If Q is more than the K equilibrium value, then it is, yeah, okay. So if K equilibrium is more, so if Q is, sorry, I keep getting myself. If Q is more than K equilibrium, then the system is going to favor the leftward reaction. So system goes left, and if Q is less than K equilibrium, then the system goes to the right. Yeah. So In this case, our Q value is bigger than our K equilibrium value, right? Our 25 is bigger than our 10. 25 is, yeah, obviously bigger than 10. Therefore, the system is not at equilibrium. It's going towards the it goes towards the leftward direction. So they told us here to calculate the concentration of all the species at equilibrium. Here, I believe we're going to do the ice table. Let me just double check. Yeah, ice table. Okay. So I'm just gonna delete all this. If you want, you can replay it. Replay the video so you can write down whatever I just wrote. How long is this? 20 minutes. We're still on question 3. Okay, I'll go faster, you guys. So, since we know the system is going to the left, right? Therefore, therefore this is going to be consumed, and these are going to be produced, right? So let's write down the ICE table. So ICE. Initially, we have. Wait. So initially, we have the concentration of H2. What is it? It's 1.00, right? So write down 1 so I can go faster. Concentration of I2 initially is also 1. Concentration of 2HI initially it's was it 5? Yeah, 5. And then the change, right? Since the system is going to the left, the products are going to be consumed and the reactants are going to be produced. Therefore, it's plus X, and minus X. Now, we're going to join these two together, and for the equilibrium, it's going to be 1 plus X, and then 1 plus X, and then 5 minus X. Now we can write down equilibrium, the equilibrium expression. So, products over reactants. So, 5 minus X, all squared, obviously, since we have the coefficient of 2, over 1 plus x times 1 plus x. 1 plus x times 1 plus x, we can just say 1 plus x squared. So 1 plus x squared. And this is equal to, since this is at equilibrium, it's going to be equal to 10. Let me just double check. Yeah, it's going to be equal to 10. So here we're solving for x. So I'm going to square root both sides to get rid of the powers. So 5 minus x over 1 plus x equals to radical 10. Cross multiply. Radical 10 plus 10. Radical 10 uh, x equals to. Am I doing this right? Yeah, equals to 5 minus x. And then just solve for x. So I'm just going to do some on my calculator on the calculator so we don't take much time. So radical 10 plus radical 10 gives 5 minus x. Yeah, that's correct. So for x, and we got that. Please be correct. We did something. Oh yeah. Oh, how did I not notice this? Okay. Here the coefficient is 2, therefore it's going to be minus 2x. My bad, guys. My bad. I completely forgot about that. That is my bad. Okay. Just go back to this and change this to 2x, so for x, and we got 0.355 or 0.356. What did they get? They they got 0.357, 0.356, same thing. So now we're going to yeah. Now we're going to find the concentrations at equilibrium, right? Right? We know x to be 0.356, right? 0.356. So now you substitute x into all of these, and you're going to get the concentration. So for I2 and for H2, since they have the same formula, it's just going to be 1 plus 0.357, 0.356 is the value I got. I'm going to use that. And then for the concentration of HI, I should have wrote down brackets, my bad. Equals to, so it's just going to be 5 minus 2x. Substitute in the x, you're going to get, so minus 5 minus 2 times 0.356. We got 4.288. I'm just going to take it to three significant figures, so 4.29. Let's double check our answers. Yeah, so 1.36 for I2 and H2, and then 4.29 for HI. I'm only gonna solve one example of ICE table in the course revision because ICE table is way too time consuming and I want this to be a short recording, unless they ask it in a different type of way in which I will solve it. So here. A sample containing 6 moles of H2 and I2 were introduced into a 3 decimeter vessel. Reaction. So this is literally just isn't just the same. This is literally just the same idea as question. Yeah, this is literally just the same idea. But here they didn't give us the concentration. Sorry, the number of moles of HI. Therefore, we know that the reaction. So I'm just gonna screenshot this real quick. And given they only gave us H2 and I2 moles, so and they didn't give us they didn't give us the number of moles of HI. Therefore, we can assume that the reaction hasn't occurred yet, so no product has been made. So it's just going to be so for this, right? It's just going to be minus x because the reactants are being consumed, so minus x, and then minus x, and then plus x, right, to produce a product because reactants they combine together in a reaction to produce a product. And you see these two arrows here, like the backwards arrow and the forward arrow. This means that this is a reversible reaction, so the reaction can go backwards. So basically, this product can be consumed to form the two original reactants we had, or vice versa. The two reactants can combine together to form the product 2HI. So we just solve as the same way we did. Just solve the same way we did last time, and yeah, that's it. Kp for NH4Cl S, so we don't consider it in the equilibrium constant formula. Plus NH3 gas plus HCl gas is, so here they give us the Kp. We're just going to find the partial pressures. This is again, it's the same idea, but I'm gonna solve it because here it's partial pressures and not concentration. And I just don't want you guys to get mixed up. So let's see here. How long is this going for? 28 minutes. Okay, we're making good progress. So solids, don't consider it. So our expression is just going to be NH3. So partial pressure of NH3 times the partial pressure of HCl equals to 1.00 times 10 to the power of negative 2 atm. No, let's just write down the. Here, I don't think you need to do ICE table because it's common sense. I'm just gonna double check. Yeah, so you don't. I mean, if you really don't know how to do this chapter, I'm gonna write down the ICE table just to explain what's going on, but you don't need to do it here because it's pretty self-explanatory. So, we have the reaction. Let's just write it down again. NH4Cl S to give NH3 plus HCl. So here uh, we don't even consider solids, and we aren't even given a pressure value for the solid. We don't consider it, so it's just initially it's nothing. And then these two, initially they're also nothing because, no, actually, wait. Yeah, initially they were nothing because anything, we weren't given any information about the partial pressure of these before the reaction has occurred, so nothing. And then we know in this case, the products get consumed, and to form the reactant gets consumed to form products. So it's just going to be minus x plus x, and I believe since this is a solid, we don't consider it. So it's just going to be, so here if we apply these two, sorry, not apply, substitute these two into this formula, right? It's going to be x times x to give 1.00 times 10 to the power of negative 2. X times x is basically x squared equals 1.00 times 10 to the negative 2. Therefore, you're just going to do the square root of all this, and you're going to get x. X is, um, was in this case, x is the partial pressure because it's just x here by itself. But say for example it was 5 plus x or like 2 plus x, you're going to substitute x into here to get the partial pressure of each one, and that's your final answer. So what is the square root of 1.00 times 10 power negative 2? It's 0.1, right? I should have thought of that. You can easily do that. Okay, so let's just double check here. The answers for partial pressure of NH3 and partial pressure of HCl is 0.1 ACl, 0.100. Now, consider the following reaction. C solid plus CO2 gas to give 2CO gas. Solid carbon and carbon dioxide gas at 1160 Kelvin were placed in a rigid 2-liter container and the reaction is represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, still some carbon solid remaining in the container. Results are recorded in the table below. Find the reaction mixture at oh sorry for I can't read for the reaction mixture at equilibrium at 1160 Kelvin. The partial pressure of the CO2 gas is 0.82. Calculate. Okay, so they told us at equilibrium. So once the reaction has stabilized and the rate of reactions for both the product and the reactants are equal, the partial pressure of CO2 is 0.82. Let's just note that down for now. I'm gonna screenshot all these and just solve them. So we're gonna use this table below. Actually, we're gonna use. Did they give us a volume? Yeah, they gave us a volume. Okay, we're gonna need this later on. So okay, so for part A1, the partial pressure of CO. Okay, so let's find the partial pressure of CO. At equilibrium. So here they give us at equilibrium. Therefore, at equilibrium, we're going to consider this value in time, right? So because this is like the final, it's the one. It's like the if you want to if you like listen, if they say equilibrium, you want and they give you a table like this, always look at the final value because that final value is going to be at equilibrium, right? Or just look at whenever the partial pressure stabilizes. So here, notice how it's 4.2 and here it's also 4.2. So yeah, but just to be on the safe side, take the final reading. So total pressure. So we know in this case we know that total. So P total is equal to partial pressure of reactant X plus the partial pressure of Y, or just partial pressure of X plus partial pressure of Y. In this case, we have a solid, don't consider that. We have a CO2 gas, and CO gas. They gave us the partial pressure of CO2 is 0.82 at equilibrium, right? So partial pressure of CO2, which is 0.82, and they want us to find the partial pressure of CO. We don't know this, so plus X equals to the P total. P total, we can get it from the table here. It says total pressure of gases in container. So we look at the value here, 4.2. So 4.2 equals to 0.82 plus X. So for X is equal to 4.2 minus 0.82 to give 3. Sure, 3.38. Yeah, okay. Now the value of the equilibrium constant, let's have a look at the reaction here. So reaction is a solid, don't consider it. Gas and gas, we consider those. Okay, so product of reactants, so P of CO all squared over the P of CO2. Here we don't have a coefficient, so it's nothing. Okay, equals to Kp. Now, what's the P of CO2? You know, P of CO2 is 0.82. So 0. No, sorry, no, P of CO. Um, it's 3.38, right? So 3.38 squared over P of CO2, which is 0.82, 0.82. So, uh, over 0.82, and we got uh, our Kp to be 13.9. I'm just gonna round it to 14. So let's see what they did. 13.9, 14. خلاص, easy. No, there's another part to this. Oh my god, okay. Here. If a suitable solid catalyst was placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final pressure of the gases at equilibrium without the catalyst? Justify your answer. Okay, so we know that catalysts, they only affect the rate of the reaction. So the the pressure of the gases will not change. It won't increase, it won't decrease, it's going to stay the same, right? So they told us to justify our answer and they asked us the question. So our answer should include the answer, is it greater than, less than, or equal to, and the justification. So here I'm going to say it's equal to. And why? It's because catalyst uh, only speeds up reaction rate. That's it. Or gives an alternative path for a reaction. Let's check their answer. A catalyst does not affect the equilibrium position, it only allows the reaction to reach equilibrium faster, so it affects the rate. So the final total pressure of the gases stays the same. خلاص, easy. Okay. Forgot. What's this? Okay. The two isomers of butane exist in equilibrium as represented by the equation below. So N minus butane gas to give isobutane gas, where Kc, what's Kc? Wait. Oh, Kc, so just K concentration. Okay. By the way, I'm just gonna write down some things for you guys. I'm gonna write them down here and I'm gonna send them as notes on the group chat. So, Kp refers to pressure. Kc refers to concentration. Kw refers to water. Ka refers to acid. Kb refers to base. And Ksp refers to an insoluble salt. Sorry if my handwriting's bad. I'm writing using a mouse. So yeah, if you see me using these, just know. If you see me using these throughout the solutions, just know that these letters stand for their respective meaning. Okay, so clearing. Yalla, let's see. Once the equilibrium was reached, the concentration of N-butane was found to be. Okay, so at equilibrium. Okay, if the volume of the system is increased to double its original volume, what will the new concentration of N-butane be after the equilibrium has been reached at 25 degrees Celsius? The volume. Wouldn't it just stay the same in this case? We're just trying. Right, okay. So, here. So, here they give us concentration, right? So, and they give us Kc, so we know that this is a the equilibrium expression for this is going to involve concentration, right? Now, what do we know the concentration formula to be? N over V. Now, here they told us that they doubled the original volume, so this was multiplied by 2, or basically the total concentration was divided by 2, right? So if they doubled the volume, means they halved the concentration. So what is the concentration of N-butane after equilibrium has been re-established? Therefore, we're just going to do 5.0 times 10 power negative 5 divided by 2 to give 2.5 times 10 power negative 5. Okay, you see their answer, and I already saw it, but yeah, 2.5 times 10 power negative, was it 3 or 5? Negative 5. Huh. Okay, here they use 5 times 10 power negative 3, and the given they told us it's 10 10 power negative 5. I don't know what's up with that, they're just acting dumb, but it's an issue from their side. Okay. Let's see how many questions you have left. Okay. So we have 9, okay, so 8, lots of parts, hello, 9, more parts, hello, 10, 11, 30. Oh, they're all parts. Great. Okay. How long has this been going for? 43 minutes, not bad, okay. Okay, so answer the following. Okay, so a sample of that mass of ASF5 is introduced into a 10.5 liter container at this temperature. What is the molar concentration? Concentration is the number of moles. So number of moles divided by volume. Here they give us the mass. Just find the molar mass from your periodic table and solve. Now, B, in terms of concentration, write the equilibrium constant for the expression of this. You guys already know how to write the equilibrium constant, equilibrium expression. So K equilibrium equals to the concentration of the products. So concentration of the products over the concentration of the reactants. When equilibrium is established, 30% of the original number of moles of ASF5 has decomposed. Calculate the molar concentration of ASF5 at equilibrium. So if right, so here we're gonna do ICE. Okay, I'm gonna solve this. Yeah, okay. So equilibrium is 30% of the moles of ASF5 has decomposed. Therefore, we have 70% remaining. But I don't think this is relevant. Calculate molar concentration of ASF5 at equilibrium. Okay, so are we given? Right, so we have to get the concentrations. Okay, what's the molar mass of ASF5? Actually, I'm just gonna use their answer. So for part A, they got 0.0156. Okay, so concentration of ASF ASF5 is equal to 0.0156. Is that correct? Yeah, 0.0156. Okay. So let's write down the formula. And let's also write down the equilibrium expression. So K equilibrium is equal to the concentration of product over reactants. So concentration of ASF3 times F2, concentration of F2 obviously, over the concentration of ASF5. Right. Okay. Wait, just gonna give me a sec. Okay. So they told us 30% decomposed, therefore 70% remains, right? So the molar concentration of ASF5 at equilibrium is just going to be 70% or 0.7 times 0.0156. So 0.0156 to give 0.01092. I'm just going to take it to three significant figures. 0.019. 0.0109, sorry. 0.0109. This is our answer for, right, so, okay, part 2. Here we're going to draw the ICE tables. We're going to form an ICE table, whatever. Yeah, okay, so AS, whenever you always write down the reaction when you're doing this, it's much easier. So ASF5 to give ASF3 and F2, where initially this was 0.0109, and then we don't have a concentration of this, and we don't have the concentration of this. And then for the change, this one was consumed to make these two. So minus x plus x and plus x. And some of you may ask, how do we know in this case if it's minus x or plus x for the ASF5? Um, Here they didn't give us the concentrations of ASF3 and F2, therefore they haven't been formed yet. So yeah, we're going to put them in this step. And yeah, now we just simplify, or just combine these two together, and combine this and this. So it's going to be 0.0109 minus x, and then nothing plus x is just going to be equal to x, and nothing plus x is going to be equal to x. We substitute these values into this. So, do it on the calculator here. So it's going to be x times x over 0.0109 minus x. So x times x is basically x squared. So x, let's do this. Okay, so x squared over 0.0109 minus x. Okay, I'm doing something wrong here. Wait. I'm doing something wrong. We don't even have K equilibrium. Equilibrium constant. Wait, let me figure out what to do here. Wait, so we can just say. Okay, I think I have an idea. Let me just double check. Yeah, okay, I was correct. Yeah, okay. Yeah, okay. So they told us that 30% was consumed, right? So 30% was consumed. Therefore, to find the concentrations of ASF3 and F2, we're going to do 30% times this, right? 30% times the original concentration of ASF5, because this 30% is the product of the reaction. So 30%, so times 0.3 equals to 0.3 times 0.0156 to give to three significant figures 4.68 times 10 to the power of negative 3, right? This is the concentration of F2 and of ASF3. So now we go to our calculator and we substitute all of this into this formula. So x times x squared, so x squared over 0.0109 minus x, where x is, in this case, x is just 4.68 times 10 power negative 3, and our k equilibrium is to three significant figures, 3.52 times 10 power negative 3. Let's double check our answer. They do. Oh, I'm so dumb. I'm so dumb, it hurts. I'm so dumb, it hurts. We're supposed to do concentrations, okay, into this formula. And we already have the concentration of ASF5. I don't know why I did minus x. So we press equal, and our K equilibrium is equal to 2 times 10 power negative 3. And yeah, 2 times 10 power negative 3, basically 1, 2, 3. 2 times 10 power negative 3, or if you round it, yeah, 0.00201. Okay. Calculate the mole fraction of F2 in the container at equilibrium. Okay, so now we know the formula for mole fraction is the so mole fraction is number of moles over number of total moles, or partial pressure. So partial pressure, which is, but here we're not given any pressure, so let's not use this formula. Okay, so the total number of moles in this case, we have, did they give us a volume value? Let's see, let's go back to the question. They gave us a volume value, yeah, they gave us a value of 10.5 liters. Okay, so volume is equal to 10.5 liters. Now we know number of, now here we're given concentration and volume. To find number of moles from that, we do C equals N over V. Now we're going to find the number of moles for all of the, so we're going to find the total number of moles and the number of moles of and the number of moles of F2. So the concentration of F2 is equal to the number of moles, which we don't know, over the volume, which is 10.5, and we know the concentration of F2, so it's just going to be 4.68 times 10 power negative 3. Solve for x, and you're going to get to three significant figures 0.0491. Okay. This concentration, so the concentration of F2 is also equal to the concentration of AS3, ASF3. So therefore, no. So wait, no, just number of moles of F2 is equal to this, which is also equal to the number of moles of ASF3. Okay. And now we want to find the number of moles of ASF5, right? ASF5 at equilibrium, we know the concentration to be, what was it, 0.0109, right? Concentration is equal to number of moles over volume. So 0.0109 over number of moles times over, so concentration equals number of moles times volume, so N over the volume, which is 10.5, N of ASF5 is equal to, so just do 0.0109 times 10.5, and I got it to be to three significant figures 0.114. Now, and total is going to be this plus this and plus this again, because it's the number of moles of this. So n total is this here, so 1 plus 2 plus this over here, 3. So 0 point, let's just clear some space here up top. So we add all these two together, so 0.0491 plus 0.0491 plus 0.114 to give us, so 0.114 plus 0.0491 plus 0.0491 to three significant figures, and total is 0.212. So 0.212, and number of moles of F2, we got it to be 0.0491. So 0.0491. So do 0.0491 divided by 0.212, and you're going to get to three significant figures, 0.232 as the mole fraction of the container at equilibrium for F2. And mole fraction doesn't have a unit because it's number of moles divided by number of moles, so cancel. Okay, let's see. Please be correct, please be. Yes, thank you. 0.23. Okay, they didn't round, so 231, 232, same thing. Okay. Damn. An hour. Great. I guess I could do like an hour for each chapter. Chapter 14 is going to be easy, and it won't take that long. Even though it's all ICE table, there's a shortcut you can apply. And then chapter 13. Oh, we're solving that right now. Okay, yeah, chapter 12 is going to be the long one in that case, because it's also the one with the most questions, no? Yeah, hello. Okay. Alright, so number 9. Consider the following: a 2 mole sample and they gave us volume. Okay, they didn't give us number of moles of H2 or Br2, so we can instantly know that it's going to be, so for the ICE table, it's just going to be minus x, and plus x. Okay, 700 Kelvin. Write the expression. Okay, I'm gonna zoom out so we can get all this in one screenshot. See a sec. Okay, the expression for equilibrium constant Kc. So gas, gas, gas. We're going to take all these into consideration. Okay, so products over reactants. Okay, I'm sure you guys know how to do this. I'm not going to waste time on this. Okay. What is the concentration of HBr at equilibrium? We're going to have to look at the graph here. So, 1 point. So let's see the increments of by how much it increases. So from here to here, it's increased by 0.4. Therefore, each increment is an increment of 0.2. So 0.2 per increment. So here it's so we can see the reaction. This is the graph of concentration versus time. So this is just like how the concentration decreases as the reaction goes on over time. We can see that the graph stabilizes at around this point here, and this point is just going to be 1.6 plus 0.2, so 1.8. So this we did. This was 1.8. Okay. Determine the equilibrium concentrations of H2 and Br2. Okay. ICE for this? I guess so. Yeah, ICE. Okay. So we're just gonna use the reaction they gave us here. I'm not gonna write it again. So I C E. Okay, whatever. Okay. So initially, the concentration of 2 HBr at equilibrium, we got it to be 1.8. Right? Oh well, initially it was 2.0, and at equilibrium it's 1.8. Okay. So this is obviously minus x because the products are being formed. They didn't give us any values for the products. Here they give us number of moles only for the HBr. And guys, I made a big mistake here. Actually, no, I didn't because we got the concentration from the graph, but um, in questions like this, you're always supposed to find the concentration first. We know concentration is number of moles divided by volume. Here they gave us the concentration from the graph, so it's fine. Okay, now, what's initially the concentration of H2? We don't know. And Br2, same goes for that. These are produced, so plus X and then plus X. Combine these two together. And also we know minus X is 0.2, right? Because it went down from 2.0. We know X is 0.2, right? Because initially the concentration of HBr was 2, and then at equilibrium it was 1.8. Therefore, X is just going to be equal to 0.2. So these here, so X is just going to be equal to 0.2. So therefore, the concentration of H2 and Br2 is just 0.2, right? No, no. Right. Okay, right. Okay, that makes much more sense, right? So, the concentration of HBr decreased by 0.2. So we could therefore say that um, so wait, x plus x is equal to 0.2, right? Where 2x is equal to 0.2, where x is equal to 0.1. Because uh, the concentration of the products formed here is going to, like, the concentration here is the same for each product because the coefficients are the same, right? Coefficient here is 1 and coefficient here is 1. Therefore, we can just do, and we know x is equal to 0.2. So when we know minus x for this one here is 0.2, so we can do x plus x equals 0.2, and x is equal to 0.1. Therefore, the concentration for H2 is 0.1, and the concentration for HBr2, sorry, for Br2 is 0.1. I explained that really badly. My bad, guys. I really hope you understood that. Okay. So on the graph below, make a sketch that shows the concentration of H2 changes. Okay, so you know that H2 initially was nothing, it was 0, and then it became 0.1, right? So on the graph, um, it was initially 0, then it leveled out at 0.1. This is our answer for that part. And then here, calculate the value of the equilibrium constant. So let's write down the formula for equilibrium constant. So Kc, let's give ourselves more space. So Kc equals to products or reactants, concentration of products, so H2 and BR2 over HBR, where the concentration of this one was 0.1, concentration of this one was 0.1, concentration of this one was 1.8. These are values at equilibrium, right? So do 0.1 times 0.1 essentially is 0.1 squared. So we go to our calculator. 0.1 squared over 1.8 gives us 0.0. What is this? Oh, okay. 5.6 times 10 power negative 3. Oh, I'm so dumb, it hurts. I'm so dumb, it hurts. I, guys, the coefficients, don't forget the coefficients, they matter, right? So this is squared. Oh, I'm so dumb, it hurts. I did not notice the coefficients in this case. Okay, can we replay that? We can. Okay, so it's going to be 0.1 squared over 1.8 squared. My bad, guys. So 3.08, so three significant figures is going to be 3.09 times 10 power negative 3. Our 3.09 is essentially 3.1 times 10 power negative 3. Okay. Okay, good question. NO2, NO, and Cl2 gases were introduced into a sealed container at initial pressures of 16 and 8 atm respectively, and allowed to react and reach equilibrium according to the equation that okay. At equilibrium, the total pressure of the gases was 24 atm. Calculate the value of Kp. Okay. So 16 and this one is 12. So the pressure of NO and the pressure of Cl2 in atm, obviously. So let's just write down the equilibrium, the Kp expression. So Kp, long K. Okay, so Kp is equal to the pressure of NOCl squared, because coefficient 2, see this time I didn't forget it, over the pressure of NO squared times the pressure of Cl2. Okay, now we don't know the pressure of NOCl, right? But they gave us the total pressure. They gave us the pressure of NO and of Cl2. Therefore, we can find the pressure of NOCl. So P total is equal to the pressure of NO plus the pressure of Cl2 plus the pressure of NOCl. So, what is P total? 24, which is equal to, what's the pressure of NO? 16, plus, what is the pressure of Cl2? 12, plus X. So for X, 16 plus 12, so 28. What? Oh, okay. These are the pressures. These pressures here are not at equilibrium. This pressure here is at equilibrium. Wait, at equilibrium. Therefore, we can't apply this formula. We're going to have to do ICE table. Okay, my bad. My bad. Let's see. So, ICE. So, ignition, change, equilibrium. So initially, the pressure of NO is, so initially it's 16, and for Cl2 it's 12. For NOCl we don't know. Then the change Here they didn't give us a pressure of NOCl2 and OCl, therefore we can assume that the products were consumed to form a reactant. So here we could say 16 minus x and 12 minus x uh, plus x, or x whatever. All of this, we could say it's equal to 24, because now this is at equilibrium, right? These are all the pressures at equilibrium. And we know all the pressures is 24. So from this, we could solve for x. So let's do this on the calculator. So 16 minus x plus 12 minus x plus x equals to 24. Solve for x, and we got the pressure. We got the pressure of NOCl to be 4. So now we could do ICE table. No, not ICE table, so we can apply this formula here to find Kp. So you could either substitute in these directly, or you can substitute x and just get a value for each of the pressures at equilibrium and then substitute into this formula. Both work. I'm just going to do it directly. So product over reactants. Okay, so we know that the product here. Okay, now guys, be careful. Um, the pressure is 4, but we have a coefficient of 2. And here the coefficient of 2 means it's squared. I nearly forgot to square it. That's why I just mentioned that. So 4 squared over pressure squared of NO at equilibrium. So pressure squared of NO. So 16 minus x. Actually, I'm not going to do that. I'm just going to find the pressures by substituting x. Then I'm going to substitute all into the calculator. So the partial pressure, so the pressure of NO at equilibrium is equal to 16 minus x, so 16 minus 4, which is 12. The pressure of Cl2 at equilibrium, which is 12 minus x, so 12 minus 4, which is 8, and the pressure of NOCl at equilibrium, we know it's 4. So now it's much easier to substitute it into calculator and solve. So NOCl squared, so 4 squared, yes, okay, thank you, over, I'm muted, I'm not, okay, over pressure of NO squared, so 12 squared, times the pressure of Cl2, which is 8, and we got, okay, so 0.0138. They got not, yeah, because I'm retarded. I'm dumb, I'm so dumb, it hurts. I did the same mistake again. You guys. But this mistake was actually much worse this time. Okay. Okay. I'm gonna stop teaching. I'm too bad for I'm too bad at this. Okay. So they told us 2 for NO and 2 for NOCl. Therefore it's minus 2x. It's plus x. And sorry, no, minus 2x minus x. And then plus 2x. So 16 minus 2x plus x. No, plus 12 minus x. No, wait. 12 minus x. And then 2x. All of this equals to 24. Let's solve for x again on the calculator. Yeah. Okay, I can't bad calculators, but yeah. 12 minus x plus 2x equals to 24. So for x, So we still got x to be 4. Okay, so the pressure, so now, the pressure of, now that we know x is equal to 4, let's find the pressures. So 16 minus 2x, so 16 minus 2 times 4, so 16, so 16 minus 8. So for NO, the pressure is 8. 12 minus 4, which is 8. And then NOCl, which is 2 times 4, which is 8. Then we substitute these values into this formula correctly this time. So 8 squared over 8 squared times 8 gives you 0.125. 0.125, that's correct. Okay. Be careful while you're solving. You're seeing these mistakes I'm making. They're it's very easy to make mistakes like this. What is this? Okay, this does not look fun. Chat, how long has this been going for? Hour and 20. Very fun. Okay. Uh, NO and CO2 gases were introduced in a steel container at initial pressures of 10 and 6. Not to react. At equilibrium, the pressure of CO2 was 2 atm. Calculate the value of Kp. This is the same idea. It's a similar idea, but this time they told us, I'm going to solve it either way. Actually, I'm not going to. Yeah, okay, I'm just going to solve it. But it's a similar idea, so you should have gotten the hang of this by now. So, uh, here we could do ICE table على طول. So ICA, and I'm not going to make the same mistake this time, so don't worry, guys. So, initially, the pressure of, here didn't give us a pressure of NOCl, so we could assume that the products are being consumed to form, the reactants are being consumed to form a product, so minus 2x, and then minus x, and then plus 2x, see? I didn't make the mistake this time. Okay, so NO initially was 10, Cl2 initially was 6 from the given, and then NOCl we don't know. The change was minus 2x, minus x plus 2x, and then 10 minus 2x, 6 minus x, and 2x. Okay, now they told us at the equilibrium pressure of Cl2 was 2 atm. Let's look at Cl2 here, so it would be this column here. So 6 minus x, 6 minus x will give us the pressure of Cl2 at equilibrium. We already know the pressure of CO2 at equilibrium is 2, so we could solve for x, and x is equal to 4. Okay, 6 minus 4, 2. So we substitute x into this one, and then we apply the mass action, the K equilibrium formula. So it's going to be the pressure of NOCl squared divided by the pressure of Cl2 times the pressure of NO squared. So let's just write that down real quick. And all of these pressures obviously at equilibrium, okay guys? So NOCl, so the pressure squared over the pressure of NO squared times the pressure of Cl. Substitute the values you got from applying x is equal to 4. What was x equal? Oh yeah, x is equal to 4. So substitute the values you get from these when substituting x is equal to 4, and you're gonna get Kp. Kp in this case is 8. Okay. Yeah, so we got x equals to 4, then you substitute the values, and you substitute x equals to 4 into these, and you're going to find the pressures at equilibrium, then you solve. Okay. 12. This question concerns the reaction. Okay, so some SO2, O2, and SO3 gases exist at equilibrium in a closed container. Predict the effect of changes of the quantity of SO3. Okay, so let's have a look at. Okay, so increasing the temperature, they told us delta H is less than 0. When delta H is less than 0, that means that this is an endothermic reaction. So to increase, so here we, I hope I don't mix this up. So here, it's negative delta H. Delta H is negative since it's less than 0. So if we increase the temperature, the system will try to decrease it. How does system decrease the temperature? By favoring the forward reaction. To consume heat, right? To consume heat or to decrease the temperature because we increased it. So predict the effect of the changes on the quantity of SO3. So if uh, if this reaction is forward, the forward reaction, sorry, if this reaction is favored, the forward reaction, if it's favored, then more SO3 will be produced. Let's look at the answer for part A. And okay, exothermic, guys, I'm dumb. Negative delta H is exothermic. I'm so dumb it hurts. I'm so dumb it hurts. I make dumb mistakes. Guys, don't make dumb mistakes with these in the exam. It's gonna mess you up, okay? So negative delta H, which means exo. Okay? So therefore we could also rewrite this reaction to look like this, which I'm gonna do because it's much easier to understand. So since they told us the reaction is exothermic, therefore we know heat is being produced, right? Or yeah, heat is being produced, so now we can answer much easier. So increasing the temperature. So if we increase the temperature, the system will try to decrease it. So to decrease the temperature, so to decrease delta H, the backwards reaction is going to be favored. Therefore, this is going to be consumed, so the quantity of SO3 will decrease. And we just saw that in the answer, the effect, so here, the quantity of SO3 will decrease. Okay, now, uh, reducing the volume of the container. So, volume of the container. Let's have a look at the number, let's have a look at the coefficients for each of the chemicals in the reactant, in the reaction. So here, if we add up the coefficients, this is 3 over 2 and this is 1. So this side has, so this side is, just know that reactants here are more, they have a higher coefficient than the products. So if we reduce the volume, the system will try to increase the volume. Therefore, we're going to be producing more of the side that has the higher coefficient. So the backwards reaction is going to be favored to produce more of these because they have a higher coefficient, which means they have a higher number of moles. I believe the coefficient is the number of moles. So the pressure is going, so the volume is going to be increased, right? Of the, like the gas molecules inside the container. So the quantity of SO3 will decrease. Let's have a look at that. And given decrease in volume, SO, what did I do wrong? A decrease in volume increases the pressure. Oh, I'm so dumb again, it hurts. Okay, I explained that completely wrong. So ignore what I just said. Okay. Okay. So we know pressure and volume, they're inversely proportional. So if you were to increase the pressure, then the volume would decrease. And if you were to increase the volume, then the pressure would decrease, correct? Here, they told us that the volume was reduced. Therefore, the pressure was increased, right? the system will try to decrease the pressure. So here in this case, um, the pressure was P was increased. Therefore, system will try to reduce the pressure. Now, the pressure, to reduce it, let's have a look at the coefficients, right? So here it's 1 and here it's 3 over 2. 3 over 2 or 1.5, I'm just going to write it as 1.5. 1.5 is greater than 1. Therefore, we're going to want, so to try to decrease the pressure, we're going to have, we're going to try to use up, no, so let me try to gather my words and then I'll say it, so because I don't want to explain something wrong. So yeah, so we want to consume more of these because they have a higher coefficient, so they have more like molecules in the container of this compared to this, right? So if you want to reduce these, then the forward reaction is going to be favored, right? And when the forward reaction is favored, these are reduced, so the quantity of these is reduced to form more of this. So therefore, more SO3 is formed. So normal, hence the quantity of SO3 will increase. Okay. Some catalyst is added. Catalyst doesn't matter because catalyst won't have an effect here because catalyst only changes the rate of the reaction. Does not have an effect on the equilibrium. So catalyst does not affect the equilibrium position. It only allows the reaction to reach equilibrium faster. Okay. Number 11. Number 11. True. Huh? Number 12 to number Allah. Great service. It's really nice. Okay, what is the effect of adding NaOH to an equilibrium system containing saturated C? Okay. So if we add NaOH, then we're going to have an increased amount of OH minus ions. Therefore, the system will try to decrease the concentration, so the backwards reaction will be favored. I hope that's correct. I hope that's correct. What is it? Yeah, adding NaOH increases OH minus, so it's going to try to decrease it. So um, yeah, the backwards reaction is favored, so more CuOH is produced. What is the effect on the percent yield of raising pressure on the following equilibrium system? So here, let's just do this real quick. So if we increase the pressure, so let's just have a look at the coefficients here. So N2, so 1 N2 plus 3 H2 to give 2 NH3. Here our total coefficients for the reactant is, for the product is 2, and here it's 4. Uh, Here the pressure was increased, therefore system will try to decrease the pressure, right? So it's going to favor the side, so it's going to consume the side with the higher coefficient, right? So the forward reaction is favored, therefore more NH3 is produced, right? And they ask us what is the effect of the percent yield. Percent yield is basically how much we got of the product from this reaction. So the percent yield was increased because more of the product was consumed. Sorry, more of the product was made because the forward reaction was favored. So let's have a look at the answer. Since more ammonia is produced, percentage yield increases. Wow, I got a question right without first time. Okay. What is the effect of the percent? What is the effect on the percent yield of raising temperature on the following equilibrium? Sure. Okay. So so let's write down the reaction. Here delta H is less than 0, so it's exothermic, so we can just write it down like this. Since the reaction is exothermic, heat is being produced. So what is the effect of raising temperature? Temperature was raised, therefore the system would try to decrease the temperature, so the backwards reaction will be favored. So in this case, the percentage yield will decrease, right? Because the products are going to be consumed here to decrease the temperature, right? Because this side has heat, we want to reduce that because heat was applied, and the temperature wants to reduce that, and the system wants to reduce that. So backwards reaction is favored. Therefore, percentage yield of the product here will decrease. So look at the answer. Percentage. Oh, oh! I got a heart attack when I saw increases and I realized it's part B. Okay. Which decreases the percentage yield? Halas, easy. Next. Two more questions. Yay. Okay. Write the expression for the equilibrium constant Kp. I'm sure you guys know how to do that. I'm gonna skip this. For reaction one. So part A we skipped it. Part B. Will the For reaction 1, will the equilibrium constant increase, decrease, or remain the same if the temperature rises above 298 Kelvin? Justify your answer. So, uh, so temperature rises above a set point, so therefore the temperature in this case was increased, right? And we're looking at reaction 1. Reaction 1, we have a positive delta H, therefore the reaction is endothermic. Right? So we could say, we can write down, we can rewrite this formula. So delta H plus X solid plus H 2O gas. Why am I writing the state symbols? Wait. Delta H plus X plus H2O gives XO and H2. So here temperature rises, so temperature was increased, so T increased. Therefore, system would try to decrease temperature. System will try to decrease temperature by uh, consuming the side that has temperature or has delta H. In this case, the reactant side has delta H, so consume it. The forward reaction would be favored. So equilibrium constant. Okay, now let's have a look at the formula of equilibrium constant. Equilibrium constant. We know that it's the product over the reactants. If the amount of the reactants decreased, right? So if so what is this here? This is Kp. Okay. So if the pressure of the reactants, let's just assume, I'm going to assume it was 1, so you guys have a better understanding of this, okay? So um, P over 1, right? This is before we increase the temperature. If we decrease, sorry, this is before we increase temperature. Now that we increase the temperature, these have been consumed. Therefore, the pressure of these will decrease, right? Therefore, uh, initially it was 1. Let's assume now it's 0.5 or something, right? And uh, when you divide by a smaller number compared to the original number you're dividing, the quotient will be bigger, right? So in this case, Kp will increase. I hope you guys understood that because that's like the best way I could explain it. If you divide by a smaller number, so I'm gonna try to like give you guys an example. So let's assume that the pressure of product was equal to 5, and the pressure of reactant was equal to 2. But then consuming after the reactants being consumed to form products, uh, the pressure at equilibrium, so more products were formed. So let's assume that the pressure here was 10, and then the pressure of the reactants, since the reactants were used up, let's assume it was 0.5. If we compare, if we compare the Kp before and after the effective temperature increase, we're going to see a bigger Kp for equilibrium, right? I'm going to solve it either way just to show you guys. So Kp, we're going to be solving for this one. So Kp before we increase the temperature is just going to be, so we made, so this is not exactly the, so this is not the expression. This expression here is not the expression for reaction 1, but I'm just going to assume it is, okay, because I can't be bothered to actually write down the reaction expression. So 5, so product over reactants, 2.5, right? This was before the effective increase in temperature. After increasing temperature, the reactants decreased and the products increased. Therefore, 10.5, this is 20. So notice how we went from 2.5 to 20. Yeah, so increasing the temperature does increase Kp. Which question is this? 14b. Increasing temperature, value of Kp will increase. Okay. Part C. Determine the value of delta H of reaction 3. Oh, is this one of those? It is one of those. Okay. I don't know how to do this. And nor do I know how to do part C. This is when you flip. So like here you want the delta H of reaction 3, so you want XO to be on the product side, and sorry, on the reactant side, and then X side and XO2 gas to be on the reactant and the product side. Why do I keep mixing up products and reactants? Oh my god. So you're just going to have to look at these two and then like flip some things around, or like multiply or divide, hess up, whatever, you know. I don't know how to do part C and D. Sorry guys. I'm just gonna show you what the marking scheme says. And yeah. Okay, here it's pretty simple. You just reverse equation 1 and equation 2. Actually, yeah, that's easy once I do that. Because if we reverse this and reverse this, it's going to be 2XO. And we're also going to have X solid in the product side. And we're also going to have XO2 on the product side. So yeah, okay. So when you reverse it, you're going to change the sign from positive to negative. So negative 131 minus no. So negative 131 plus negative 41. So it's just going to be negative 172 kilojoules per mole. Now part D, I actually don't know how to do. So yeah, expression of what is this? Determine K. Is this actually the answer? Okay. You know what? I don't know what they're trying to do here. Wait, let's see. The products in this case are X solid and XO2. Yeah, no, I don't know this. I can't help you guys. Sorry. Okay, number 15. This is a top question. That's it. Okay. Hello. Continue the Lewis dot structure. Okay. Let's continue Lewis dot structure. Part B is similar to that one question we did, which was like 30% and 70%, so I don't think I'm gonna do this again, because I want the recording to be short. And they give you some things here, given like pressure, volume, 0.82. So I'm just gonna continue the Lewis dot structure and then khalas. So let's calculate the total number of valence electrons. So 1 plus 6 plus 4 plus 6 plus 4 plus 4 plus 1 plus 1 plus 1 plus 1 plus 1. So 6H, so 6H, and then 3 carbons and 2 O's. So yeah, CH3, C3, H6O2. Yeah, so 12 plus 12 plus 6, 30. Okay, so equals to 30. So we want the total number of electrons in them to be 30. So let's just connect all these at first. And let's complete the octets. So 1, 2, 3, 1, 2, and then 1. Okay, now let's count how many electrons we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So here we have 32. We need to reduce by 2. So we're going to form a double bond. We're going to remove 2 pairs and add a pair. So let's just see where we can do this. Okay. So we can't do this because if we do this, right, then C is going to have 2, 4, 6. No, wait, that's fine. Wait. No, I did this question in class before, and I know I did something that made me get it wrong, so let me just double check here. Yeah, okay. Wait, no. Okay, I believe the Lewis dot structure would just look something like this. Form a double bond here. And yeah, I think that's it. Let's double check. Yeah, okay. Got it correct. Good. And part B is similar to what I explained earlier in that question, so it should be fine. So ICE table, yeah. Okay, do I do chapter 14 in one video too and just finish it? Because chapter 14 is pretty straightforward. Let me see. This recording has been going on for an hour and 48. And I'm still home alone, so I could record this. I mean, so many questions though. 19. But these questions don't have lots of parts. So in reality, it's like 2 pages worth of questions, like 3 pages, whatever. Okay. I'll do these in a separate. Okay, I'll do chapter 14 in a separate video for the people that want chapter 14 help only. So in that case, that was chapter 13 solved. I hope you guys benefited from this, and good luck in your studies.